Have you ever stood outside on a clear night, looking up at the stars, and felt a sense of certainty about how the universe works? For generations, we've built our understanding of space on a set of core assumptions, ideas so deeply ingrained that we often take them for granted. We assume that dark matter is made of invisible particles, that black holes are simple cosmic vacuums, that the speed of light is an unbreakable barrier. But what if these foundational beliefs aren't just incomplete? What if they're completely wrong? It's a startling thought, but one that astronomers and physicists are confronting more and more as new data pours in from telescopes, satellites, and simulations. Mysteries are piling up: unexplained gravitational anomalies, conflicting measurements of cosmic expansion, particles that shouldn't exist behaving in ways they shouldn't behave. Step by step, observation by observation, the clean and comfortable story we've told ourselves about the cosmos is beginning to fray at the edges. And in those frayed edges, something extraordinary is being revealed, not just gaps in our knowledge, but the possibility that we've been looking at the universe through the wrong lens altogether. In this video, we're going to explore 20 of these core assumptions about space that may be dead wrong. We'll venture into the heart of modern cosmology, from the nature of time and the fabric of space-time itself to the puzzling roles of dark matter and dark energy. We'll reconsider the birth of the universe, the behavior of black holes, and even our search for alien life. This isn't about dismissing science, it's about celebrating it. Because science at its best isn't a collection of answers. It's a living, breathing conversation fueled by curiosity, doubt, and the courage to ask what if. By the time we're done, you won't just see the night sky differently. You'll understand why questioning everything we think we know is the only way to uncover truths deeper and more wonderful than we ever imagined. For nearly a century, one of the most fundamental pillars of cosmology has been the idea that the universe is expanding at a steady, predictable rate. This concept, first observed by Edwin Hubble, gave us the Hubble constant, a single, elegant number meant to describe how fast galaxies are rushing away from us. It became the bedrock of our cosmic measuring tape, allowing us to calculate the age of the universe, trace its history back to the Big Bang, and project its future. We built our entire understanding of cosmic evolution on this assumption of a constant, uniform expansion. But what if that bedrock is beginning to crack? Recent observations from our most powerful telescopes have unveiled a puzzling discrepancy, a cosmic rift that has astronomers both baffled and exhilarated. On one side, we have meticulous measurements from the Planck mission, which mapped the ancient afterglow of the Big Bang, the cosmic microwave background. Planck's data provides a snapshot of the infant universe and suggests a specific, rather sedate value for the Hubble constant. On the other side, the Hubble Space Telescope has been meticulously studying the contemporary universe, observing pulsating stars and stellar explosions in nearby galaxies to directly measure how fast they are moving away from us. Its results consistently point to a significantly faster rate of expansion. This isn't a small margin of error. It's a stubborn and growing gap that has withstood years of re-examination and improved measurements. Scientists have given this tension a dramatic name, the Hubble tension. It's more than just a technical disagreement between two datasets. It is a direct challenge to our standard model of cosmology, the so-called lambda-CDM model. This model, which incorporates dark energy and cold dark matter, has been incredibly successful at explaining the large-scale structure of the universe. But the Hubble tension suggests it might be incomplete or perhaps even wrong in a fundamental way. So what could be causing this rift? astronomers are exploring several revolutionary possibilities. One compelling idea is that dark energy, the mysterious force driving the universe's accelerated expansion, is not the constant, static force we've assumed it to be. Perhaps it's dynamic, growing stronger over time, or interacting with dark matter in ways we haven't yet imagined. Another possibility is that our understanding of gravity itself needs an update on the largest scales. Einstein's theory of general relativity has been proven correct time and again within our solar system, but maybe it breaks down when applied across billions of light years. There are even more exotic suggestions, like the existence of a new type of subatomic particle in the early universe that altered its expansion history. The implications of this are staggering. If the Hubble constant isn't constant at all, it forces us to reevaluate everything. Our estimated age of the universe, roughly 13.8 billion years, could be thrown into question. Our predictions for the ultimate fate of the cosmos, whether it will end in a heat death, a big rip, or a big crunch, would need a complete overhaul. This single discrepancy is a powerful reminder that the universe is under no obligation to conform to our elegant models. It is a dynamic, evolving, and deeply mysterious place, and our journey to understand it is far from over. The Hubble tension isn't a problem to be solved. It's a doorway inviting us to step through and discover a new, deeper layer of cosmic reality. For nearly half a century, the leading explanation for dark matter has been a hypothetical entity known as a WIMP, a weakly interacting massive particle. The idea is beautifully simple and compelling. These particles would be their own antimatter opposites. They wouldn't interact with light, and their immense numbers would have been forged in the fiery heat of the Big Bang, naturally accounting for the amount of dark matter we observe. It's a theory so elegant that it has dominated the field, guiding the construction of immense, ultra-sensitive detectors buried deep underground in mines and mountains, all designed to catch the faintest whisper of a WIMP collision. But after decades of listening, these exquisite experiments, with names like LUX, Xenon, and Panda X, have heard nothing but silence, not a single unambiguous signal. The great WIMP hunt, for all its ingenuity and hope, has so far come up completely empty. This persistent lack of detection is forcing a profound and exciting shift in the world of physics. Scientists are now broadening the search, considering possibilities that are far stranger than a single, shy particle. One intriguing alternative suggests dark matter could be made of actions, ultra-lightweight particles that would behave less like discrete bullets and more like a pervasive, rippling wave flowing through the cosmos. Other theorists are revisiting the idea of primordial black holes, not the giant ones we find at galactic centers, but countless numbers of tiny black holes, each no heavier than an asteroid, forged in the first chaotic moments after the Big Bang. These ancient relics would be invisible, would clump under gravity, and could potentially explain the dark matter we infer. Perhaps the most radical proposal is that we don't need to find a new particle at all. This idea, known as modified Newtonian dynamics or MUND, suggests that our understanding of gravity itself is incomplete. Instead of invoking invisible matter, MUND proposes that gravity behaves differently at extremely low accelerations, like those found in the outskirts of galaxies. This modification could, in theory, explain why the outer stars of galaxies rotate just as fast as the inner ones without needing any dark matter, glue to hold them together. While MUND has its own set of challenges, particularly in explaining the behavior of galaxy clusters, its persistence highlights just how deep the mystery runs. The stakes of this puzzle could not be higher. Our entire understanding of how the universe assembled itself is built upon the gravitational scaffolding provided by dark matter. Computer simulations of cosmic evolution rely on it to form the web-like structure of galaxies we see today. If dark matter turns out to be something else, a family of particles, ancient black holes, or even a sign of revised physics, it would send us back to the drawing board on everything from the birth of the first galaxies to the ultimate fate of the cosmos. The invisible majority of the universe is refusing to be pigeonholed, reminding us that nature's imagination far exceeds our own. Yet the reality revealed by cutting-edge science is infinitely more complex and fascinating. Far from being simple cosmic trash compactors, black holes are now understood as dynamic engines that profoundly reshape the space, time, and matter around them. One of the most profound challenges to the old view came from Stephen Hawking's revolutionary work in the 1970s. He proposed that black holes aren't completely black after all. Due to bizarre quantum effects occurring right at the edge of the event horizon, pairs of virtual particles can pop into existence. Normally, these particles would instantly annihilate each other, but if one falls into the black hole while the other escapes, the escaped particle becomes real, carrying away a tiny bit of the black hole's mass. This slow leak, known as Hawking radiation, means that given enough time, an almost unimaginable amount of time, a black hole can actually evaporate and vanish. This idea single-handedly shattered the concept of a black hole as a permanent, unchanging prison, introducing a life cycle that ends not with a bang, but with a whisper of radiation. Our view of these objects was transformed yet again in April 2019, when the Event Horizon Telescope collaboration unveiled the first ever direct image of a black hole's shadow. The world watched in awe as the supermassive beast at the heart of the galaxy Messier 87 was revealed, not as a simple dark circle, but as a brilliant, asymmetric ring of light surrounding the dark abyss. This glowing ring is the signature of superheated gas and plasma being accelerated to nearly the speed of light just outside the point of no return. The image confirmed that black holes are not passive holes but active, energetic systems. Many supermassive black holes, including the one at the center of our own Milky Way, also fire out colossal jets of matter and radiation that extend for thousands of light years. These jets can regulate star formation in entire galaxies, heat the gas in galaxy clusters, and essentially act as some of the most powerful engines in the universe. This leads to a truly mind-bending possibility. What if black holes are not the ultimate endpoints of information, but rather transformers or even gateways? The famous black hole information paradox highlights this puzzle. Quantum mechanics states that information about a particle can never be truly destroyed. But if you throw something into a black hole and it later evaporates via Hawking radiation, which appears to be random and featureless, what happened to all the information that object contained? This paradox has forced physicists to consider extraordinary solutions. Some theories suggest the information is encoded on the surface of the event horizon, a concept known as the holographic principle, where a three-dimensional volume is described by a two-dimensional surface. Others, like the ER equals EPR conjecture, propose a link between black holes and wormholes, suggesting that the interior of a black hole might be connected to another region of space-time or even another universe entirely. In this view, matter isn't destroyed, it's transferred or transmuted. This radical rethinking of black holes forces us to confront the very nature of reality. They are no longer seen as destructive monsters but as potential keys to unifying the two great pillars of modern physics, Einstein's general relativity, which governs the very large, and quantum mechanics, which governs the very small. The intense gravity and quantum effects at a black hole's boundary are a natural laboratory for testing theories of quantum gravity. Understanding how black holes work, how they store information, and how they eventually die could provide the crucial clues we need to see the universe not as a collection of separate parts, but as a single, coherent, and astonishingly connected whole. Yet for all its power, Einstein's cosmic speed limit has never completely extinguished humanity's dream of reaching the stars. And in the decades since, physicists have begun to explore tantalizing loopholes in the rules, not by breaking the law, but by bending it. One of the most famous of these concepts is the Alcubierre warp drive, first proposed by physicist Miguel Alcubierre in 1994. This ingenious idea doesn't involve propelling a ship through space faster than light. Instead, it imagines a spacecraft sitting inside a bubble of flat spacetime, while the fabric of the universe itself is manipulated ahead of and behind the craft. In front of the bubble, spacetime would be compressed, pulling the destination closer. Behind it, spacetime would be expanded, pushing the point of origin farther away. In this scenario, the ship itself remains motionless inside the bubble, not accelerating at all, and thus avoiding the relativistic penalties of mass increase and time dilation. The bubble of spacetime, however, could in theory move at effectively superluminal speeds. It's a concept that turns the entire problem inside out, suggesting that the key to interstellar travel isn't building faster engines, but learning to harness the very structure of reality. Of course, the practical challenges are immense. The Alcubierre drive requires forms of matter with negative energy density, something we have only seen in tiny, quantum-scale demonstrations like the Casimir effect. The energy requirements are staggering, potentially needing the equivalent of a Jupiter-sized mass converted to pure energy. And there are serious concerns about the buildup of hazardous radiation at the front of the warp bubble. But the mere fact that such a solution is mathematically permissible within general relativity is a profound revelation. It shifts the conversation from a flat prohibition on faster-than-light travel to a complex engineering puzzle. It tells us that the universe's rulebook might be more flexible than we ever imagined, offering backdoors and workarounds that await our understanding. Perhaps the most mind-bending challenge to the finality of light speed comes not from relativity, but from its great rival, quantum mechanics. The phenomenon of quantum entanglement, which Einstein himself famously dismissed as spooky action at a distance, presents a bizarre form of instantaneous connection. When two particles become entangled, their properties are linked in such a way that measuring the state of one particle immediately determines the state of the other, no matter how far apart they are. This seems to suggest that some form of information is traveling between them faster than light. However, most physicists argue that this doesn't violate causality or allow for useful faster-than-light communication because the outcome of the measurement is fundamentally random. You can't use it to send a deliberate message like a radio signal. The spooky action remains a private conversation between the particles. Even more curiously, experiments in quantum tunneling have shown that particles can appear to spend less time traversing a barrier than a photon of light would take to cross the same empty space. This gives the illusion of superluminal speed, but again, most interpretations conclude that no actual information is transmitted faster than light in a way that could create a time travel paradox or break causality. These quantum effects don't punch a hole in Einstein's theory so much as they highlight its limits. They show us that the universe has layers of connectivity that operate outside our everyday experience of space and time. The cosmos might be threaded with a hidden quantum fabric that allows for correlations and connections that, while not useful for sending messages, hint at a deeper, more instantaneous unity beneath the surface of reality. If any of these possibilities, wormholes, warp drives, or quantum entanglement, were ever harnessed, even in principle, the implications would be nothing short of revolutionary. Our galaxy, which currently seems like an impossibly vast ocean, would suddenly become a navigable archipelago. The search for extraterrestrial life would take on new urgency as the distances that once isolated us became bridgeable. Our entire cosmological perspective would shift from seeing the universe as a cold, empty, and isolating expanse to recognizing it as a potentially connected and accessible network. The greatest barrier to exploration may not be a law of physics carved in stone, but a limitation of our own imagination. The speed of light may be the law of the land, but we are just beginning to learn how to read the fine print. This deeply ingrained feeling that time is a universal constant, a steady drumbeat for the entire cosmos, is perhaps one of our most stubborn illusions. We schedule our lives by it, we measure the ages of stars with it, and we instinctively believe that a second for us is a second for everyone and everything, everywhere. But over a century ago, Einstein's theory of relativity shattered this comforting notion, revealing time to be not a rigid backdrop but a flexible, dynamic dimension woven into the very fabric of spacetime. The closer you are to a massive object like a planet or a star, or the faster you travel, the more time itself slows down relative to a distant observer. This isn't a theoretical quirk, it's a measurable reality. The GPS satellites orbiting Earth have to constantly correct their clocks for this precise effect. Their time runs slightly faster than ours on the surface because they are farther from Earth's gravitational pull. Without this correction, your navigation system would guide you into a field within minutes. So time isn't just relative, it's personal, shaped by your own state of motion and your place in the gravitational landscape of the universe. Yet even Einstein's revolutionary framework may only be part of the story. When we push our theories to their absolute limits, to the moment of the Big Bang or the heart of a black hole where gravity becomes incredibly strong and the realm becomes incredibly small, the equations of general relativity break down. This is where the quest for a theory of quantum gravity begins, and it is here that the nature of time becomes more bizarre than ever. Some approaches, like loop quantum gravity, propose that space and time are not smooth and continuous but are instead composed of tiny, discrete grains or loops, a kind of quantum foam at the smallest possible scale. In this view, time might not flow like a river but might instead advance in tiny, indivisible steps, much like the frames of a film. Other theories, like string theory, suggest that what we perceive as time could be an emergent property arising from the complex interactions of more fundamental, timeless entities. The mind-bending implication is that time, as we experience it, might not be a fundamental feature of the universe at all. It could be an illusion, a useful narrative constructed by our consciousness from a deeper, timeless reality. We're not just theorizing about these possibilities, we are actively searching for evidence. Astronomers use the universe's most precise natural clock's pulsars to test the fabric of spacetime itself. These rapidly spinning neutron stars send out beams of radiation with the metronomic regularity of a cosmic lighthouse. By monitoring networks of these pulsars across the galaxy, scientists can listen for the faintest whisper of a disturbance in the force, a ripple in spacetime caused by a passing gravitational wave. But they are also looking for something even subtler. Tiny, anomalous variations in the ticking of these clocks that could hint at a grainy structure to spacetime or other quantum gravitational effects. It's a painstaking search, like trying to hear a single wrong note in a symphony playing across thousands of light years, but a single positive result would revolutionize our understanding of reality. If time is indeed emergent and not fundamental, it forces a profound philosophical shift. Our entire conception of cause and effect, of history, and even of free will is built upon the arrow of time. We see the universe as a narrative unfolding from a beginning to an end. But if time is a surface-level phenomenon, then this entire story might be a kind of projection. The past, present, and future could all exist simultaneously in a static, four-dimensional block universe, with our conscious experience merely tracing a path through it. This doesn't make our experience less real, but it does suggest that the true nature of the cosmos is far stranger and more magnificent than our everyday perception allows. The question is no longer just what time is, but whether the flow of time is the central drama of the universe or merely the lens through which we, as conscious beings, are able to perceive it. This belief that the rules are written in stone and apply identically from one end of the cosmos to the other is known as the principle of the uniformity of nature. It's the bedrock upon which we've built all of modern cosmology. It's why we can look at the light from a galaxy 10 billion light-years away and feel confident that the atoms there absorb and emit light in exactly the same way as the atoms in our laboratories. It's an assumption so fundamental that we rarely even stop to question it. But what if it's not entirely true? What if the universe's rulebook has a few regional additions? A central pillar of this idea is the constancy of the fundamental constants, those seemingly arbitrary numbers that define the strength of nature's forces. Take the fine structure constant, often denoted by the Greek letter alpha. This number determines the strength of the electromagnetic force, governing how tightly electrons bind to atoms and how those atoms interact with light. For decades, we've measured it here on Earth and assumed its value was, well, constant, unchanging, a fixed feature of reality. But when astronomers train their most powerful telescopes on the most distant, ancient objects in the universe, extremely bright quasars powered by supermassive black holes, they see something peculiar. The light from these quasars has traveled for billions of years to reach us, and on its journey, it passes through immense clouds of interstellar gas. These clouds imprint a unique fingerprint on the light, a series of dark absorption lines that tell us exactly what elements are present and how their atoms are behaving. Several independent teams analyzing this ancient light have reported a faint but persistent anomaly. The spacing between these absorption lines seems to suggest that the value of the fine structure constant in those distant regions of space and time was ever so slightly different than it is today. In one direction of the sky, it might appear weaker, in another, slightly stronger. The discrepancies are tiny, on the order of a few parts in a million, and the scientific community is still vigorously debating whether this is a real physical effect or some subtle systematic error in the observations. But if it is real, the implications are staggering. It would mean that the laws of physics as we know them are not universal and eternal. They could evolve. They could have been different in the past, or they might vary from one giant supercluster of galaxies to another. This directly challenges the Copernican principle, the idea that there is nothing special or privileged about our place in the universe. If the fundamental constants are indeed variable, then we must confront a dizzying possibility. Perhaps we live in a very specific cosmic neighborhood where the constants are set to just the right values to allow for the existence of atoms, stars, planets, and life. Other regions of the multiverse or even our own universe might be governed by a completely different set of rules, rendering them barren and unrecognizable. We wouldn't be at the center of the universe in a geographical sense, but we might be in a very special physical niche, a hospitable bubble in a much vaster and more varied cosmic landscape. The ripple effects of this would touch every branch of science. Our search for extraterrestrial life would have to expand its parameters, considering that biology might operate under entirely different chemical rules in other parts of the cosmos. Our models of particle physics would need to account for a potentially dynamic vacuum of space that can slowly alter the forces we feel. Even our understanding of the universe's history would be up for revision, as a varying constant could have altered the rates of nuclear reactions in the early universe and the life cycles of the first stars. The very notion of a single, grand, unifying theory of everything would be thrown into question, replaced by the humbling prospect of a patchwork universe, a cosmos of infinite variety where the only true constant is change itself. We often picture the depths of space as the ultimate emptiness, a perfect, silent vacuum where matter is so sparse that between galaxies, you might find only a single atom in a volume the size of a bedroom. This image of a barren, static void is a powerful one, reinforced by countless sci-fi movies showing the cold, black emptiness between the stars. It's an assumption that feels intuitively right. But modern physics paints a radically different picture, one where so-called empty space is in fact the most dynamic and energetically rich thing in the entire universe. It is not a void but a vibrant sea, teeming with fleeting, ghostly activity and dominated by a mysterious force we are only beginning to comprehend. This revolutionary view springs from the bizarre world of quantum mechanics. According to quantum field theory, what we perceive as empty space is anything but, at the tiniest conceivable scales, space is a chaotic foam of energy. Pairs of virtual particles and their antiparticles, electrons and positrons, quarks and antiquarks, are constantly flickering into and out of existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other and paying the energy back. This isn't just a mathematical abstraction. We can actually observe its effects. The most famous demonstration is the Casimir effect. Imagine two uncharged, perfectly smooth metal plates placed incredibly close together in a vacuum. In the seemingly empty space outside the plates, every possible wavelength of these virtual particles can fluctuate, but in the narrow gap between the plates, only certain wavelengths can fit. This creates a pressure imbalance, and the greater pressure from the outside actually pushes the plates together. It's a measurable, macroscopic force generated purely by the roiling energy of the quantum vacuum. Empty space, it turns out, is so alive with activity that it can push physical objects around. But the quantum foam is just the beginning. When we zoom out to the grandest cosmic scales, we find that space is filled with something even more enigmatic and powerful: dark energy. This isn't a substance made of particles, it's a property of space itself. Einstein first proposed a similar concept, the cosmological constant, as a fudge factor to keep the universe static. He later called it his greatest blunder, but modern astronomy has resurrected the idea in a stunning way. Observations of distant supernova in the late 1990s revealed that the expansion of the universe isn't slowing down due to gravity, as everyone expected. It's accelerating. Something is acting as a form of anti-gravity, pushing galaxies apart at an ever-increasing rate. That something is dark energy, and it's not a minor component. It makes up about 68% of the entire mass energy content of the cosmos. The vacuum of space isn't inert. It's imbued with a repulsive force so dominant that it dictates the ultimate fate of the entire universe. This realization that space is an active medium, not a passive stage, opens up incredible possibilities and profound questions for the future of science and exploration. For spacecraft navigation on long interstellar voyages, even the faintest whisper of this quantum vacuum could potentially impart a tiny, cumulative drag or affect ultra-precise measurements, requiring new models to account for the medium they're traveling through. More speculatively, if we could ever learn to manipulate the energy density of the vacuum, to somehow dampen or amplify these quantum fluctuations, it could theoretically open the door to unimaginable energy sources or even propulsion concepts like the Alcubierre warp drive, which requires engineering the vacuum of spacetime itself. Yet this vibrant vacuum also contains a potential cosmic threat, a concept known as vacuum decay. The Higgs field, which gives particles their mass, exists in a particular energy state that makes our universe stable. But some theories suggest this might not be the true, lowest energy state of the vacuum. It could be a false vacuum, like a ball resting in a small valley on the side of a much deeper hill. If a quantum event somewhere in the universe were to trigger a transition to the true vacuum, it would create a bubble of new, fundamental physics that expands at the speed of light, rewriting the laws of nature and obliterating everything we know in its path. While this is highly theoretical, it underscores a profound shift in perspective. The emptiness of space is not a neutral nothing. It is a state of being, and its stability is what allows our reality to exist. The Great Void is in fact the central character in the cosmic story, a dynamic and potent frontier that holds the keys to both our deepest understanding and our most speculative dreams. We've built our modern understanding of the cosmos on the rock-solid foundation of Einstein's general relativity. For over a century, it has been our most powerful tool for describing the force of gravity, passing every experimental test with flying colors. It predicted the bending of starlight around the sun, the existence of black holes, and the precise timing of GPS satellites. It gave us a breathtaking vision of gravity, not as a mysterious pull, but as the curvature of spacetime itself, a cosmic landscape where planets and stars simply follow the contours of this warped geometry. It feels like a complete and triumphant theory, but this profound success masks a deep and growing crack in the foundation, a fundamental incompatibility that physicists have been struggling with for generations. General relativity, which rules the world of the very large, and quantum mechanics, which governs the realm of the very small, are mathematically and philosophically irreconcilable. When we try to combine them to understand the core of a black hole or the first moment of the Big Bang, the math explodes into infinities and nonsense. This isn't a minor technicality. It's a screaming signal that our understanding of gravity, for all its power, is incomplete. This tension isn't just theoretical. It shows up in real-world observations that stubbornly refuse to fit the elegant mold of Einstein's equations. Take the curious case of the Pioneer anomaly. For decades, as the Pioneer 10 and 11 probes journeyed toward the outer solar system, scientists noticed they were slowing down just a tiny bit more than predicted by all known gravitational forces. The discrepancy was minuscule, equivalent to a gentle acceleration toward the Sun, about 10 billion times weaker than the gravity we feel on Earth, but it was persistent and unexplained for years. While most of this anomaly was eventually attributed to the subtle, uneven radiation of heat from the spacecraft's power systems pushing them off course, the episode served as a powerful reminder. It showed that even in our own celestial backyard, gravity might still have a few secrets left to reveal, and that we must be extraordinarily careful before declaring any mystery solved. A much larger and more significant challenge comes from the motions of entire galaxies. According to general relativity and the observed amount of visible matter, stars orbiting at the outskirts of a spiral galaxy should be moving much more slowly than those near the center. But when astronomers measure these rotation curves, they find that the outer stars are whipping around just as fast as the inner ones. The predominant solution for this has been to invoke the gravitational glue of dark matter, an invisible substance that provides the extra mass needed to hold these fast-moving stars in their orbits. But after decades of searching, we still haven't directly detected a single particle of this dark matter. This persistent failure has led some scientists to pursue a radically different path. Perhaps our equations for gravity are simply wrong on the vast scales of galaxies. This alternative approach is known as modified Newtonian dynamics, or MUND. First proposed by physicist Mordechai Milgrom in the 1980s, MUND suggests that gravity behaves differently at extremely low accelerations, like those experienced in the far reaches of a galaxy. It posits a subtle change to the laws of motion that would kick in when gravitational acceleration falls below a certain threshold. Remarkably, with just this one tweak, MUND can accurately predict the rotation curves of many galaxies without needing any invisible dark matter at all. It's an elegant and compelling idea. However, MUND has its own significant challenges. It struggles to explain the observed behavior of galaxy clusters, and most critically, the bullet cluster collision, where the gravitational effects observed seem to be clearly separated from the visible matter, strongly suggesting the presence of some kind of collisionless, invisible mass. While MUND may not be the final answer, its very existence is crucial. It acts as a necessary counterweight, forcing the mainstream scientific community to continually question its assumptions and prove that dark matter is not just a convenient placeholder for our ignorance. The dawn of gravitational wave astronomy has given us an entirely new sense with which to probe the universe, but it too is presenting new puzzles. When the LIGO Observatory detected ripples in spacetime from colliding black holes, it was a spectacular confirmation of general relativity's predictions. Yet, the properties of the black holes that are merging their surprisingly large masses and their rapid spin alignments are not always what our standard astrophysical models predicted. Each new event catalogued adds more data points, and some of these points are starting to look like outliers. Could these subtle anomalies be hints of something deeper? Perhaps they are clues about the nature of gravity itself in these most extreme environments, tiny deviations from Einstein's predictions that could point the way toward a more complete theory of quantum gravity. This is the ultimate goal, the holy grail of modern physics, a theory that seamlessly unifies gravity with the other three fundamental forces of nature, the electromagnetic, strong, and weak forces. This theory of everything would work equally well for the subatomic quantum world and the cosmic scale of galaxies. String theory and loop quantum gravity are two leading contenders, but both remain frustratingly theoretical, lacking any experimental proof. The failure to achieve this unification after so many decades of trying suggests a humbling possibility. The flaw may not be in our mathematics, but in our very concept of what gravity is. Perhaps gravity is not a fundamental force at all. The groundbreaking idea of emergent gravity, proposed by physicists like Eric Verland, suggests that gravity is not a primary ingredient of the universe but a secondary, emergent phenomenon. In this view, gravity is a consequence of the universe's tendency toward disorder, an entropic force that arises from the way information is stored on the holographic boundary of space-time, much like how the pressure of a gas emerges from the chaotic motion of countless molecules. It's a radical departure from everything we've assumed, suggesting that the force that shapes the cosmos is itself a shadow of a deeper, information-based reality. The next great breakthrough in understanding gravity might not come from staring at the equations on a blackboard, but from listening closely to the faint, unexpected whispers from the edges of our understanding, carried on the ripples of a black hole collision or in the silent, swift dance of a star on the far side of a galaxy. For centuries, the story of our cosmic origins seemed to have a clear and dramatic opening line, the Big Bang. We've all seen the iconic illustration, a single, infinitely dense point suddenly exploding into being, igniting the furnace of creation and setting the stage for everything that would follow: galaxies, stars, planets, and us. It's a powerful and compelling narrative, a Genesis story for the scientific age that gives our universe a definitive starting point, a moment of birth some 13.8 billion years ago. This assumption that the Big Bang was the absolute beginning, the ultimate first cause, is woven deeply into our popular understanding of cosmology. But what if this entire framework is wrong? What if the question, what happened before the Big Bang, isn't a meaningless paradox but the most important question we can ask? The standard Big Bang theory is incredibly successful at describing the evolution of the universe from a fraction of a second after that initial event onward. It explains the observed expansion, the abundance of light elements, and the existence of the cosmic microwave background radiation. However, the theory itself is silent on the moment of the bang itself. The equations of general relativity break down at that point of infinite density and temperature, a singularity where our known laws of physics simply give up. This isn't just a gap in our knowledge, it's a fundamental boundary. The Big Bang theory describes the aftermath of the beginning with stunning accuracy, but it has nothing to say about the beginning itself or what, if anything, came before. It's like finding a perfectly detailed diary that starts on page 2. This profound limitation has led physicists to propose breathtaking alternatives that completely do away with the idea of a singular beginning. One of the most intriguing is the concept of a cyclic or bouncing universe. Imagine the cosmos not as a one-shot explosion, but as a perpetual cosmic lung, expanding and contracting in an endless cycle. In this model, our current expanding universe might eventually be halted and reversed by the collective gravity of all matter, leading to a big crunch. But instead of collapsing into nothingness, this collapse could rebound in a new, big bounce, fueled by quantum effects that prevent a true singularity. The universe would be born again from the ashes of the previous one, in an endless cycle of death and rebirth that stretches infinitely into the past and future. In this view, the Big Bang wasn't a beginning. It was simply the latest turning of a page in an eternal story. Another radical idea emerges from the realm of quantum gravity and string theory, the multiverse. If our universe is just one bubble in a vast, frothing cosmic foam of universes, each with its own distinct physical laws and properties, then the Big Bang loses its status as the ultimate beginning. It becomes a local event, the moment our particular bubble of spacetime inflated into existence. In this eternal multiverse, new universes could be constantly budding off from others, perhaps through processes involving black holes or quantum fluctuations in a pre-existing vacuum. There is no single beginning for the whole of reality, only countless individual origins for each constituent universe. Our entire cosmic history, from the Big Bang to the present day, becomes just one chapter in a much grander and potentially infinite meta-narrative. Perhaps the most mind-bending proposal of all comes from attempts to apply quantum mechanics to the cosmos itself. The quantum principle that something can come from nothing, or more accurately, from a quantum fluctuation in a vacuum, has been applied to the origin of the entire universe. In this scenario, the universe could have spontaneously tunneled into existence from a state of literally nothing. No space, no time, no matter. This isn't a physical process in time. It's a quantum transition that would have created time itself. If this is true, then asking what was before is a category error, like asking what's north of the North Pole. There was no before, because time began with the event. This doesn't make the Big Bang the absolute beginning in a classical sense, but rather a transition from a timeless, pre-geometric state into the space-time we inhabit. If any of these alternatives gain traction, the implications are truly revolutionary. It redefines our cosmic origins from a single, finite event to something potentially without start or end. It forces us to shift the question from "how did the universe begin?" to the far more profound and unsettling, do beginnings and endings even have a meaningful place in our description of ultimate reality? This isn't just an academic exercise. The answer determines the ultimate fate of everything. A universe with a true beginning might have a definitive end, whether in heat, death, or a big rip. An eternal cyclic or multiverse model suggests that life and consciousness in some form could persist forever, finding a way in some universe somewhere, always. Letting go of the Big Bang as the absolute beginning doesn't diminish the mystery of our existence. It expands it, opening a door to a cosmos of infinite possibility and eternal renewal, where the greatest story ever told has no first page and will have no final chapter. When we dream of finding life beyond Earth, our imagination often paints a familiar picture. We envision beings that might look different, perhaps with more limbs or unusual features, but we fundamentally assume they operate on the same biological principles we do. They would need liquid water, use carbon as the building block of their cells, and have a genetic code like our DNA to pass on information. This assumption, known as carbon chauvinism, is deeply ingrained in our search strategies. Our rovers on Mars diligently search for signs of past or present water. Our space telescopes are tuned to identify planets orbiting within the Goldilocks zone of their stars, where temperatures are just right for liquid water to exist on the surface. We are, in essence, looking for a second Earth because we assume that life everywhere must follow the same recipe that worked here. But what if this assumption is the very thing blinding us to a universe teeming with life that is utterly, profoundly alien? The element carbon is a phenomenal foundation for life because it can form strong, stable bonds with many other atoms, creating the long, complex chains necessary for proteins and genetic material. However, it is not the only element in the periodic table with such talents. Directly beneath carbon sits silicon, which shares some similar chemical properties. In theory, silicon could also form the backbone of complex molecules, potentially creating life with a very different biochemistry. Imagine a world where strange, crystalline structures slowly grow and shift under an alien sun, their metabolism based on silicon chains instead of carbon. While silicon-based life faces significant challenges such as silicon dioxide, its waste product being a solid sand rather than a gas like carbon dioxide, it is a powerful reminder that our chemistry is not the only possible chemistry. The universe might be filled with life forms for whom water is a deadly poison and oxygen is a corrosive toxin. Beyond alternative elements, there is the vast potential of alternative solvents. Water is an incredible solvent, but it is not unique. On a frigid moon like Saturn's Titan, where temperatures plunge to -180 degrees Celsius, water is frozen solid as hard as rock. But rivers and lakes of liquid methane and ethane flow across its surface. Could life evolve in those chilly hydrocarbon seas? Instead of water-based cells, organisms might have membranes made from flexible acrylonitrile polymers, floating in liquid methane and breathing hydrogen instead of oxygen. Their entire biological clock would tick at a vastly slower rate, and their internal chemistry would be unlike anything we've ever conceived. Similarly, beneath the icy crusts of moons like Europa and Enceladus, vast global oceans might be heated by tidal forces. While we hope to find water there, the immense pressure and potential chemistry could give rise to life that thrives in total darkness under conditions of extreme pressure, using chemosynthesis around hydrothermal vents in ways that make even Earth's most extreme extremophiles seem tame. This narrow focus on Earth-like life doesn't just limit our imagination, it actively limits our search for extraterrestrial intelligence. The SETI program, which listens for radio signals from the stars, operates on the assumption that an intelligent species would develop technology similar to our own and choose to broadcast its presence across the galaxy. But what if a truly alien intelligence communicates through modulated neutrino beams, gravitational wave pulses, or something we haven't even discovered yet? Our search parameters are a mirror we hold up to the cosmos, and right now, we are only looking for our own reflection. By clinging to the assumption that aliens must be like us, we risk dismissing the faint, strange signals that could be the very evidence we seek, simply because they don't fit our expected template. The exciting consequence of abandoning this assumption is that it explodes the concept of the habitable zone. A planet doesn't need to be a cozy, Earth-like world orbiting a sun-like star to host life. A rogue planet, ejected from its star system and drifting through the cold, dark interstellar void, might retain a subterranean ocean heated by radioactive decay in its core. The thick, nitrogen-rich atmosphere of a Pluto-like dwarf planet or the high-pressure, superheated surface of a Venus-like world could, in theory, host life forms unimaginable to us. The universe suddenly becomes a much more target-rich environment. Every time a mission like the James Webb Space Telescope finds a new exoplanet that seems utterly hostile by our standards, we should now ask a new question: hostile to whom? The discovery of even a single microbe on another world that uses a different biochemistry would be one of the most profound discoveries in human history. It would not just confirm that we are not alone, it would reveal that we are living in a cosmos of breathtaking creativity, where life can spark into existence in countless different ways under countless different suns. Letting go of our Earth-centric view is the first step toward truly seeing the universe for what it might be, a garden of infinite and wonderful variation. Yet for all its elegance and explanatory power, the theory of cosmic inflation finds itself in a precarious position, celebrated as a cornerstone of modern cosmology, while still lacking the definitive, smoking gun evidence that would cement its place in the history of science. The core idea is profoundly simple and compelling. In the first fleeting fraction of a second after the Big Bang, the universe is thought to have undergone a period of exponential, faster-than-light expansion, ballooning from a subatomic speck to something much larger in an almost unimaginably short burst. This incredible growth spurt would have ironed out any primordial wrinkles, explaining why the universe appears so remarkably uniform in every direction we look. It also provides a natural mechanism for the origin of all structure. The tiny quantum fluctuations stretched to cosmic size during inflation became the gravitational seeds for every galaxy, star, and planet we see today. It's a beautiful, almost necessary story, but is it true? The hunt for conclusive proof has centered on a specific signature imprinted on the oldest light in the universe, the cosmic microwave background. As the first atoms formed and the universe became transparent, this primordial radiation began its journey across space. Inflation predicts that the violent expansion would have generated powerful gravitational waves, ripples in the fabric of space-time itself. These waves, in turn, would have subtly polarized this ancient light in a specific, swirling pattern known as primordial B-mode polarization. Finding this pattern would be like discovering the fossilized fingerprint of inflation itself. The scientific community held its breath in 2014 when the BICEP-2 telescope team announced they had detected this signal. For a brief, exhilarating moment, it seemed the final piece of the puzzle had fallen into place. But the celebration was short-lived. Further analysis revealed that the signal was almost entirely due to interstellar dust within our own galaxy, a cosmic mirage that had fooled the most careful observers. Subsequent, more sensitive experiments like the Planck satellite have continued to search, but the definitive whisper of those primordial gravitational waves remains elusive, a ghost in the cosmic machine that we have yet to capture. This persistent lack of direct evidence has not killed the theory, but it has opened the door for a vibrant and healthy debate, encouraging cosmologists to explore bold and imaginative alternatives. One such idea is string gas cosmology, which emerges from the complex landscape of string theory. In this model, the universe begins as a hot, dense, and chaotic gas of the fundamental strings proposed by the theory. The properties of this gas naturally lead to a period of slow, stabilized expansion that can explain the uniformity and flatness of the universe without requiring a rapid inflationary burst. It's a radically different starting point that sidesteps some of the more philosophical problems of inflation, offering a new narrative for our cosmic dawn. Another compelling challenger is the ekpyrotic scenario, which paints a picture not of a single universe being born, but of a cyclical cosmos. The name comes from the Greek word for conflagration, or fire, and the model suggests our universe was born from a colossal collision between two three-dimensional brains existing in a higher dimensional space. Think of it like two sheets of paper smashing together in a void. This collision would have deposited an enormous amount of energy, which we now experience as the hot, dense state of the Big Bang. In this view, the smoothness of our universe isn't due to a rapid inflation, but because the colliding brains were themselves flat and uniform. This model naturally creates a universe that is large, flat, and homogeneous, and it does so without requiring the exotic physics of a singular inflationary field. It also presents a breathtaking vision of an eternal cycle, where universes are born and reborn through these cosmic collisions in an endless, higher dimensional dance. The stakes of this scientific debate are incredibly high, reaching far beyond academic curiosity. If inflation did not occur, or if it happened in a drastically different way than our leading models suggest, it forces a fundamental rethink of our cosmic origins. Our entire understanding of the initial conditions that gave rise to the galaxies would be up for revision. Furthermore, one of the most speculative yet fascinating consequences of some inflationary models is the prediction of a multiverse, an infinite froth of bubble universes, each with its own distinct physical laws. If inflation is wrong, the theoretical foundation for this vast and unobservable multiverse crumbles, pulling us back from the edge of infinite copies and recentering our universe as a single, possibly unique entity. The ongoing search for the truth about our universe's first moment is a powerful demonstration of science at its best, a field alive with competing ideas, driven not by dogma, but by a relentless curiosity to look beyond our most cherished assumptions and peer, however dimly, into the ultimate dawn of everything. For decades, the humble neutrino was considered the ultimate minimalist of the particle world, a near-nothingness that barely interacted with the universe it zipped through. These ghostly particles, produced in the nuclear furnaces of stars and in vast quantities during supernova explosions, were thought to be utterly massless, traveling at the speed of light and completely unchanging from the moment they were born. This assumption was so deeply embedded in the standard model of particle physics that it seemed unshakable. Neutrinos were the silent, weightless, and immutable spectators to the cosmic drama. But as is so often the case in science, the most profound revolutions begin with the faintest of whispers. The story of the neutrino is a stunning reminder that the universe's smallest details can hold the keys to its largest mysteries, and that what we dismiss as insignificant might be the very thing that overturns everything. The first crack in this assumption appeared not in a giant particle accelerator, but deep underground, in a place where scientists could shield their sensitive detectors from the constant cosmic chatter of the surface world. Researchers were trying to solve a puzzle about the sun, Our understanding of nuclear fusion predicted a certain number of electron neutrinos should be streaming from the Sun's core. But for years, experiments on Earth were only detecting about a third of that expected number. The question was terrifyingly simple. Were our models of the Sun wrong, or was something happening to the neutrinos on their journey? The answer, confirmed by the brilliant work at Japan's Super Kamiokande and Canada's Sudbury Neutrino Observatory, was nothing short of revolutionary. The neutrinos weren't disappearing, they were changing. They were oscillating between three different identities or flavors: electron, muon, and tau neutrinos as they traveled through space. And this phenomenon of neutrino oscillation has one absolutely crucial requirement. The particles must have mass. A massless particle, by the very rules of relativity, must travel at light speed and cannot experience time, which means it cannot change. The fact that neutrinos oscillate proves beyond any doubt that they have a tiny but real mass. This discovery shattered a core pillar of the Standard Model and earned a Nobel Prize, forcing physicists to rewrite the textbooks. The implications of this tiny mass ripple out across the entire cosmos. These ghostly particles are so unimaginably abundant that their collective gravitational influence, however faint from each individual particle, has helped to shape the large-scale structure of the universe. In the first seconds after the Big Bang, the universe was so hot and dense that neutrinos were trapped, bouncing around like photons in a fog. When they finally streamed free, their energy and motion affected how matter began to clump together, ultimately influencing the distribution of galaxies and the vast cosmic web we see today. Furthermore, neutrinos play a starring role in the most violent events in the universe. When a massive star collapses in a supernova, an astounding 99% of its energy is released not in light, but in a tremendous burst of neutrinos. These particles carry away the star's final breath, and by studying their flavors and energies, we can essentially perform a cosmic autopsy, peering directly into the heart of the explosion to understand the mechanics of stellar death. They are the universe's most efficient messengers from the most extreme environments, but the neutrinos' secrets may be even deeper and more profound. One of the greatest mysteries in physics is why our universe is made almost entirely of matter with very little antimatter. The Big Bang should have created equal amounts of both, which would have annihilated each other, leaving behind a universe of pure energy. Something must have tipped the scales. Neutrinos might be the answer. Physicists are intensely investigating whether neutrinos are their own antiparticles, a hypothetical class of particles known as Majorana particles. If this is true, it would allow for a rare process called neutrinoless double beta decay, which would violate a fundamental symmetry of nature and help explain the matter-antimatter asymmetry. Finding evidence for this would be a discovery on par with the Higgs boson, opening a window into physics far beyond the Standard Model. There's even the tantalizing possibility that these elusive particles could be the key to unlocking the nature of dark matter. While neutrinos themselves are not the dark matter, they move far too fast to be the cold, dark matter that structures the cosmos. They could be interacting with it in ways we haven't yet imagined. If dark matter particles can occasionally decay into neutrinos, or if neutrinos can help us map the gravitational wells of dark matter halos, they could act as our guides into the dark sector of the universe. The next generation of neutrino observatories, like the colossal ice cube detector at the South Pole and the proposed Dune experiment, are not just looking for neutrinos, they are using them as probes to ask the most fundamental questions about the nature of reality. From the nuclear heart of the Sun to the explosive death of stars, and from the first second of the Big Bang to the invisible scaffolding of the cosmos, the story of the neutrino teaches us a powerful lesson. Never underestimate the significance of the small and the silent, for they often hold the loudest truth. This deeply ingrained belief that the universe is fundamentally the same everywhere is more than just an assumption. It's a foundational pillar of modern cosmology known as the cosmological principle. It states that on the largest scales, the universe is both isotropic, meaning it looks the same in every direction, and homogeneous, meaning matter is evenly distributed throughout space. This principle is the reason we feel confident applying the same physical laws to a galaxy 10 billion light-years away as we do in our own labs. It allows us to model the cosmos as a smooth, expanding fabric, and it's the very bedrock upon which our entire standard model of the universe is built. But what if this bedrock is showing cracks? What if, when we finally map the cosmos in sufficient detail, we discover that it isn't a uniform tapestry but a patchwork of irregularities, with structures so vast they challenge the very idea of cosmic sameness? The most direct challenge to this principle comes from the discovery of gargantuan structures that seem to defy the expected size limits of a homogeneous universe. The most famous of these is the Hercules Corona Borealis Great Wall, a colossal filament of galaxies stretching over an astonishing 10 billion light-years. To put that incomprehensible scale into perspective, this single structure is so large it would take a beam of light, the fastest thing in the universe, 10 billion years to travel from one end to the other. That is a significant fraction of the entire age of the universe itself. According to our current understanding, such enormous formations simply shouldn't have had enough time to form under the influence of gravity alone since the Big Bang. Its existence suggests that the initial conditions of the universe might have been far more lumpy and irregular than inflation theory predicts, or that some unknown force helped to sculpt matter on scales we are only beginning to comprehend. It's as if we were studying the ocean, assuming it was a uniform body of water, only to suddenly discover a single wave taller than the distance between continents. Beyond these immense assemblies of galaxies, there are even stranger, more subtle anomalies etched into the oldest light we can see, the cosmic microwave background. This faint afterglow from the Big Bang is our most powerful snapshot of the infant universe, and it appears remarkably smooth, but upon incredibly precise inspection, cosmologists have found peculiar, large-scale patterns that are deeply puzzling. The most famous of these is nicknamed the Axis of Evil, a somewhat dramatic title for a mysterious alignment of temperature fluctuations across the sky that seem to point in a preferred direction. In a truly isotropic universe, there should be no such special axis. The patterns should be random and without any discernible alignment. The presence of this axis suggests that the early universe might have had a preferred orientation, a fundamental lopsidedness that has been frozen into the fabric of space-time ever since. Some have even speculated, though it remains highly controversial, that this could be a faint imprint of a larger multiverse, a gravitational tug from a neighboring universe that brushed against our own in the first moments of creation. If these anomalies are real and not just statistical flukes or measurement errors, the implications would ripple through every corner of cosmology. The cosmological principle is not a minor detail. It is the starting assumption for almost every equation we use to describe the universe's evolution. If we abandon it, we must also abandon the elegant simplicity of our standard model. Our measurements of dark energy, the nature of dark matter, and even the very curvature of space could all be thrown into question, as they all rely on the universe being smooth and uniform. We would be forced to consider that our little corner of the cosmos might be atypical, that we reside in a special region that isn't representative of the whole. This would be a modern Copernican revolution, not displacing us from the center of the universe, but but from a center of cosmic normality. This profound uncertainty is the very engine driving the next generation of astronomical surveys. Projects like the European Space Agency's Euclid Telescope and the Vera-C Rubin Observatory in Chile are designed to create maps of the universe with unprecedented depth and detail, charting the positions and movements of billions of galaxies. They are not just looking for new planets or stars, they are conducting a grand census of the cosmos, searching for the slightest deviations from homogeneity that could point toward new physics. They are probing the shadows of the largest structures, measuring the subtle distortions caused by dark matter, and searching for any other hint that the universe might be textured in ways we never dreamed. The quest to confirm or shatter the cosmological principle is more than an academic exercise. It is a fundamental inquiry into the true architecture of reality, a reminder that our most basic assumptions must always be tested against the deep and patient observation of the sky. Perhaps no concept in all of science fiction captures our imagination quite like the wormhole, a cosmic shortcut, a tunnel through the fabric of space-time connecting two distant points in a single, miraculous step. We see them in movies and read about them in books, and for most of us, they reside firmly in the realm of fantasy, a convenient plot device with no basis in real science. This assumption that wormholes are pure science fiction feels like common sense, but here's the astonishing truth. The math not only allows for them, it practically predicts them. The first wormhole solution emerged from Einstein's equations of general relativity in 1935, discovered by Einstein himself and his colleague Nathan Rosen. They were analyzing the mathematical description of a black hole and found that the equations also described a bridge, an Einstein-Rosen bridge, connecting to another region of space or even a parallel universe. This wasn't fiction, it was a direct, albeit shocking, consequence of our best theory of gravity. For decades, these structures were considered little more than mathematical curiosities, because the original Einstein-Rosen bridge was deemed unstable and impassable. It would snap shut faster than any signal or object could traverse it, effectively making it useless for travel, but the seed was planted. The universe's rulebook, as written by Einstein, contained a clause for tunnels through space. The question shifted from, are they possible, to, could we ever make one work? The key to unlocking a traversable wormhole, one that a person or a spacecraft could actually journey through, lies in a bizarre and hypothetical form of matter known as exotic matter. Unlike the normal matter that makes up our world, which exerts positive energy pressure and attracts via gravity, exotic matter would have negative energy density and negative pressure. This strange substance would exhibit repulsive gravity, effectively propping the throat of the wormhole open against its natural tendency to collapse. While it sounds like pure fantasy, we have actually seen glimpses of negative energy in the lab on a quantum scale. The Casimir effect, where two uncharged metal plates in a vacuum are pushed together by the energy fluctuations of empty space itself, demonstrates that regions of negative energy density can and do exist, albeit in incredibly tiny amounts. The engineering challenge, of course, is monumental. To stabilize a wormhole large enough for a person to walk through might require harvesting the negative energy equivalent of Jupiter's mass. It's a hurdle so vast that it keeps the concept firmly in the theoretical realm, but it's a hurdle of engineering, not of fundamental physics. The laws of the universe do not explicitly forbid it. The connection between wormholes and the fabric of reality grew even deeper and more profound with a groundbreaking proposal known as the ER=EPR conjecture. This idea, put forward by physicists Juan Maldacena and Leonard Susskind, proposes a stunning link between two of the most bizarre concepts in physics: wormholes Einstein-Rosen bridges, or and quantum entanglement named after Einstein, Podolsky, and Rosen. Quantum entanglement is that spooky action at a distance where two particles become linked, instantly influencing each other no matter how far apart they are. The AR equals EPR conjecture suggests that this weird, instantaneous connection might be physically realized through a microscopic wormhole bridging the particles. In this view, entanglement isn't a mysterious force acting across a distance. It's a literal geometric connection in the fabric of space-time itself. The particles aren't communicating faster than light. They are, in a sense, already touching through a higher dimensional tunnel. If this is true, then wormholes aren't just rare cosmic anomalies. They could be everywhere, woven into the very quantum foundation of the universe, forming the fundamental substrate of connectivity that makes reality a single, entangled whole. If a stable, traversable wormhole could ever be created or found, the implications would utterly revolutionize our place in the cosmos. Interstellar travel would be transformed from a multi-generational nightmare into a simple step through a doorway. A wormhole could connect Earth to a planet orbiting a star in the Andromeda Galaxy, 2.5 million light-years away, as if they were adjacent rooms. But the strangeness doesn't stop with space travel. It extends to time itself. According to general relativity, the ends of a wormhole could be manipulated. If one mouth of the wormhole was taken on a high-speed journey near the speed of light or placed near a strong gravitational field, time would dilate for that end relative to the stationary end. Upon returning, the two mouths would be out of sync. Walking through in one direction might take you to the past, while walking through the other might take you to the future. This doesn't just create a time machine. It creates the potential for devastating causal loops and paradoxes, like the famous grandfather paradox, where you could go back in time and prevent your own birth. The fact that these paradoxes arise is part of why many physicists believe nature might have a fundamental law preventing the creation of such time-traveling wormholes, perhaps through a mechanism we haven't yet discovered. While the practical creation of a human-sized wormhole remains a distant dream, the theoretical pursuit is anything but frivolous. It forces us to push our understanding of gravity, quantum mechanics, and the nature of space-time to their absolute limits. Each equation written to describe a stable wormhole is a probe into the deepest laws of the universe, testing the boundaries between the possible and the impossible. The journey from seeing wormholes as a science fiction trope to recognizing them as a serious theoretical possibility is a powerful lesson in keeping an open mind. It shows us that the universe is far more malleable and strange than our everyday experience suggests, and that the wildest ideas of today, born from the pages of Einstein's notebooks and the speculations of visionary physicists, might one day become the foundational science of tomorrow. The bridge between fiction and reality is itself a kind of wormhole, and we are only just beginning to peer into its depths. Our own solar system has long been the textbook example of how planets are born. We have a neat, orderly story. A swirling disk of gas and dust coalesces around a young star, with rocky, terrestrial planets forming close in where it's hot, and giant gas and ice giants forming farther out where it's cold. The planets all orbit in the same direction, in roughly the same flat plane, following the rotation of that primordial disk. It's a clean, almost clockwork model of cosmic construction, and for a long time we assumed it was the universal rulebook. But the discovery of planets around other stars, exoplanets, has completely upended this tidy narrative, revealing a cosmos of planetary diversity so wild and chaotic that our solar system now looks less like the standard model and more like a cosmic outlier, a singularly well-behaved member of a much more unruly family. Consider the very first exoplanets found orbiting a sun-like star, a discovery that itself was a massive shock to the system. These were not gentle giants like Jupiter, orbiting at a safe and stately distance. They were hot Jupiter's gas giants of immense size, orbiting blisteringly close to their stars, completing a full revolution in mere days. In our solar system, this would place them well inside the orbit of Mercury, a region far too hot for gas to condense. Their existence immediately posed a fundamental challenge. How could a giant planet form in a place where the building materials should have been boiled away? The answer seems to be that planets are not necessarily born where they currently reside. These behemoths likely formed much farther out, in the cooler regions of their systems, and then migrated inward over millions of years, dragged by interactions with the leftover gas and dust in the disk or with other planets. This revelation of planetary migration was the first major crack in the assumption of a standard, orderly process, showing that a solar system is not a static sculpture but a dynamic, evolving system where planets can embark on vast journeys. The surprises didn't stop there. Our solar system has nothing between the size of Earth, the largest rocky planet, and Neptune, the smallest gas giant. But out in the galaxy, there is an entire class of worlds that bridges this gap: super-Earths and mini-Neptunes. These planets, which are several times the mass and size of our own world, are among the most common types we've found. But what are they? Are they massive rocky planets with thin atmospheres, or are they primarily gaseous worlds with small, solid cores? This isn't just a question of classification. It cuts to the heart of planet formation. Their prevalence suggests that the process of building planets can easily create worlds that simply have no analog in our own cosmic backyard, filling in a gap in the planetary family tree we didn't even know was missing. Their existence suggests that the line between a rocky world and a gaseous one is far blurrier and more dependent on local conditions than we ever imagined. Perhaps the most dramatic departure from our solar system's orderliness is the discovery of planets on extreme, chaotic orbits. We have found worlds that orbit backwards, moving in the opposite direction of their star's rotation, a direct violation of the standard disk model. We have found planets with wildly tilted orbits, some even perpendicular to the star's equator, as if they were rolling around the star's poles rather than circling its waist. And most haunting of all, we have evidence of rogue planets, worlds utterly untethered from any star, drifting alone through the cold, dark interstellar void. These orphans were likely violently ejected from their home systems during a period of gravitational instability, a cosmic billiards game where young planets scattered off one another, with the loser flung into the abyss. The fact that such rogue planets may outnumber stars in our galaxy tells us that the process of building solar systems can be incredibly violent and destructive, not the gentle, sedate accumulation we once pictured. All of this chaos has a direct and profound impact on one of humanity's oldest questions. Are we alone? The search for Earth-like habitable worlds has always been guided by the idea of a Goldilocks zone, the region around a star where temperatures are just right for liquid water to exist on a planet's surface. But if planets can migrate dramatically after they form, a world that looks perfectly positioned for life today might have spent its fiery youth careening through the inner system as a hot Jupiter, sterilizing any possibility of life before settling into a more temperate orbit. Conversely, a frozen world born in the outer reaches could be nudged inward into the habitable zone, perhaps carrying with it a rich supply of water ice from the outer system to become an ocean world. The potential for habitability becomes less about a planet's current address and more about its entire turbulent history. Furthermore, the presence of a massive gas giant like Jupiter in our own system is thought to have acted as a gravitational shield, deflecting comets and asteroids that might have otherwise made catastrophic impacts on Earth. But in a system with migrating giants or planets on eccentric orbits, such a protective influence could easily become a destructive one, with large planets hurling cometary material toward the inner worlds, triggering extinction-level events instead of preventing them. Each new exoplanet discovery from telescopes like TESS and the James Webb Space Telescope adds another brushstroke to this new, messier, and far more fascinating portrait of cosmic creation. We are learning that there is no single recipe for building a solar system. The process is a complex ballet of physics, chemistry, and gravity that can produce an astonishing variety of outcomes depending on the mass of the star, the composition of the disk, and the chaotic gravitational interactions between forming planets. Our own serene and stable solar system, once the model for all others, now appears to be a special case, a peaceful suburb in a galaxy filled with planetary metropolises of incredible variety and wild, chaotic histories. This doesn't make our home less special. It makes the universe as a whole infinitely more creative, a place where the possibilities for worlds are limited only by the laws of physics and not by our own narrow experience. Of all the ideas in modern cosmology, the multiverse is perhaps the most dazzling and controversial. It's often dismissed as the ultimate act of scientific speculation, a flight of fantasy that places countless other universes beyond our own, forever hidden from view and immune to any form of observation or experiment. This assumption that the multiverse is inherently untestable and therefore not real science is a powerful and common critique. If we can't see these other universes, can't interact with them, and can't even in principle prove they exist, then isn't the whole idea just philosophy or metaphysics dressed up in the language of physics? For many, the answer is a resounding yes, but this criticism, while grounded in a healthy respect for empirical evidence, might be selling human ingenuity short. A growing number of cosmologists are now exploring ways that the multiverse could, in fact, leave its fingerprints on our own observable universe, transforming the idea from pure speculation into a potentially testable scientific hypothesis. The journey toward a testable multiverse often begins with the theory of cosmic inflation. This idea, which proposes a period of exponential expansion in the universe's first moments, doesn't just explain the smoothness and flatness of our cosmos. Some versions of it naturally lead to a multiverse. In the model of eternal inflation, the rapid expansion doesn't stop everywhere at once. Instead, it continues forever in the background, while in local pockets, the inflationary energy decays, each one bubbling off to become a separate, self-contained universe with its own Big Bang. Our entire observable cosmos would be just one such bubble in an endless, frothing sea of universes. The key question is, if our bubble universe collided with another one in the distant past, could that colossal impact have left a scar on the oldest light we can see? Cosmologists have calculated that such a collision would create a distinct circular pattern of temperature variations in the cosmic microwave background, an imprint on the sky that we could, in theory, search for. While the initial excitement around a specific anomaly in the Planck satellite data has since faded, the search for these cosmic bruises continues. The mere fact that we can define what such evidence would look like moves the multiverse from the realm of pure philosophy into the domain of potentially observable science. Beyond the search for collision scars, other multiverse theories make even more subtle predictions. The string theory landscape, for instance, suggests that the numerous possible ways for the extra dimensions of string theory to curl up upon themselves could each correspond to a different universe with its own unique set of physical laws and constants. In this vast landscape, we simply live in one of the universes where the constants are right for our existence. This is the anthropic principle in action. But how could we ever test this? Some physicists suggest that the precise value of dark energy in our universe might be a clue. If our universe is just one of many, the amount of dark energy we measure shouldn't be uniquely special. It should be a random value from a distribution of possibilities. Finding that our value is atypically small, but not impossibly so, could be interpreted as indirect statistical evidence that we are part of a larger multiverse where such values can vary. It's a subtle form of evidence, to be sure, but it's a prediction nonetheless, one that future observations of dark energy could either support or challenge. Perhaps the most futuristic test involves gravitational waves, the ripples in spacetime first detected by LIGO. The initial moments of inflation, if it occurred, would have generated a background hum of primordial gravitational waves that still permeates the cosmos. The specific frequency and strength of this signal are deeply tied to the energy scale at which inflation happened. If we can one day detect this primordial gravitational wave background with observatories like the proposed Big Bang Observer, its properties could tell us which model of inflation is correct. And since certain inflationary models are the very ones that produce a multiverse, confirming one of those models would provide powerful, albeit indirect, evidence that our universe is part of a much larger multiversal structure. We wouldn't be seeing the other universes directly, but we would be confirming the mechanism that creates them. The profound implication of finding any such evidence is that it would completely revolutionize our place in the cosmos. It would mean that the fundamental constants of nature, the strength of gravity, the mass of an electron, the power of the nuclear forces, are not deeply necessary truths written into the fabric of reality. They would be more like local bylaws, the arbitrary outcome of a random draw in our particular cosmic bubble. Some other universe might have stronger gravity, making stars burn out in a flash, or a weaker nuclear force, preventing atoms from ever forming. The conditions for life would be incredibly rare, making our universe a fortunate oasis in a vast and mostly barren multiversal desert. This idea doesn't diminish our significance. Instead, it reframes the question of why the universe is the way it is. We are no longer asking, why are these laws so perfect for life, but rather, what does it mean that we find ourselves in one of the universes that is? This relentless drive to find ways to test the untestable is a magnificent testament to the scientific spirit. It pushes the very boundaries of what we consider to be science, challenging us to develop new methods of inquiry and new definitions of evidence. The multiverse hypothesis forces us to confront the limits of direct observation and to consider whether statistical predictions, cosmic imprints, and the confirmation of generative mechanisms can ever be enough to validate a theory about realities beyond our own. It is a grand and ongoing experiment not just in cosmology, but in the philosophy of science itself, proving that even our most exotic and far-reaching ideas are not immune to the rigorous, evidence-based scrutiny that defines our quest to understand the universe. Yet the future of space travel is not solely dependent on gargantuan engineering projects. Some of the most promising near-term breakthroughs are happening at the smallest scales. Consider the ambitious vision of Breakthrough Starshot, a project that aims to send a fleet of gram-scale, wafer-thin probes to our nearest stellar neighbor, the Alpha Centauri system, within a single generation. The concept is breathtakingly simple in theory, yet revolutionary in practice. A powerful ground-based array of lasers would focus a beam of light onto the delicate light sails attached to each tiny probe, accelerating them to 20% the speed of light in a matter of minutes. At that velocity, the journey of over 4 light-years would take just about 20 years. This isn't science fiction. It's a serious research and engineering initiative backed by leading scientists and substantial funding. While the challenges are immense, from perfecting the laser array and crafting the incredibly durable light sails to ensuring the probes can transmit data back across such a vast distance, Starshot represents a fundamental paradigm shift. It proves that we are already thinking beyond the rocket, leveraging breakthroughs in photonics and materials science to conceive of missions that would have been pure fantasy just a decade ago. This approach redefines the very payload of exploration, suggesting that our emissaries to the stars may not be hulking spacecraft carrying human crews, but clouds of intelligent, networked microprobes spreading out like seeds on the interstellar wind to explore entire star systems in detail. Looking even further over the horizon, the most transformative possibilities lie in concepts that sound like they belong solely in the realm of theoretical physics, but which are grounded in serious scientific inquiry. The idea of harnessing zero-point energy, the seething, low-level energy of the quantum vacuum itself, remains highly speculative, but it hints at a future where propulsion is no longer about carrying fuel, but about tapping into the innate energy of space. More concretely, the continued theoretical work on warp drives, following Miguel Alcubierre's groundbreaking model, shows that warping spacetime itself to achieve effective faster-than-light travel is not forbidden by the known laws of physics. The monumental obstacles, chiefly the requirement for exotic matter with negative energy density, are currently insurmountable, but they are challenges of engineering and discovery, not fundamental physical impossibilities. The ongoing research in these areas is not a waste of time. It is an essential investment in stretching the boundaries of what we believe is possible. Every equation solved, every new material discovered, and every quantum phenomenon better understood brings us one incremental step closer to a future where the galaxy is within our reach. This ongoing revolution in propulsion technology does more than just promise shorter travel times. It fundamentally alters the human relationship with the cosmos. Overcoming the tyranny of the rocket equation would dissolve the psychological and physical barriers that have kept us confined to our solar system. It would transform humanity from a species that briefly visits space into a truly spacefaring civilization, with the potential for permanent settlements on Mars, thriving outposts in the outer solar system, and eventually voyages to other stars. The cultural, philosophical, and biological implications are staggering. It could lead to the branching of human civilization into distinct societies adapted to different worlds, the discovery of alien life, and an unprecedented era of exploration and discovery that would redefine our place in the universe. The assumption that space travel must always be slow is not just a technical limitation, it is a mental cage. The collective work of scientists and engineers around the world is not merely building better engines, it is picking the lock on that cage, offering us a glimpse of a future filled with light and wonder, waiting just beyond the next breakthrough. For most of us, the term cosmic rays conjures up an image of a simple, invisible beam of radiation, a natural form of background static from the cosmos. It's easy to assume they are just another type of high-energy particle, a celestial cousin to the X-rays in a doctor's office or the gamma rays from a nuclear decay. This assumption reduces them to a mere curiosity, a footnote in the grand story of the universe. But this simplistic view is a profound mistake. Cosmic rays are not a uniform shower of simple particles. They are a chaotic and immensely powerful barrage of atomic nuclei, protons, helium, and even heavier elements hurtling through space at nearly the speed of light. They are the universe's shrapnel, blasted across unimaginable distances by the most catastrophic events in existence, and they carry with them secrets that continue to baffle the world's brightest physicists. The greatest enigma surrounding these particles is where exactly they come from. For lower energy cosmic rays, we have a strong suspect: the shock waves of supernova explosions. As a star dies in a titanic blast, it can create expanding shells of gas that act like natural particle accelerators, boosting protons and other nuclei to fantastic speeds. But for the highest energy cosmic rays, the ones carrying energies millions of times greater than anything produced in the Large Hadron Collider, the story becomes much murkier. These ultra-high energy particles are so rare that only a handful strike each square kilometer of Earth's atmosphere per century. When they do, they create massive air showers, cascades of secondary particles that rain down over a wide area. Tracing these particles back to their source is like trying to find the origin of a single, specific raindrop in a hurricane. Their paths are bent and scrambled by the magnetic fields that permeate interstellar and intergalactic space. Some of these cosmic bullets seem to originate from active galactic nuclei, the intensely luminous cores of galaxies powered by supermassive black holes consuming vast amounts of matter. Others might come from colliding galaxies or perhaps even more exotic phenomena we have yet to imagine. The fact that we cannot definitively pinpoint the engines that create these particles is a glaring gap in our understanding of the high-energy universe. The mystery deepens because the existence of these ultra-high-energy particles appears to defy a fundamental cosmic speed limit known as the Gzk cutoff. Proposed by physicists Greisen, Zatsepin, and Kuzmin in the 1960s, this theory states that protons traveling across the universe with such immense energy should interact with the photons of the cosmic microwave background, the leftover radiation from the Big Bang. These interactions would sap their energy over long distances, meaning that any cosmic ray proton we detect above this energy threshold should have originated from somewhere relatively nearby within our own galactic neighborhood. Yet we have detected them, and they seem to come from all directions, including from voids of empty space where no known powerful astrophysical object resides. This is more than just an observational puzzle. It is a direct challenge to our models of particle physics and astrophysics. It suggests that these particles might be something other than protons, perhaps the nuclei of heavier elements like iron that can travel farther. Or it could point to entirely new physics operating at energies we cannot hope to replicate on Earth. These cosmic rays are not just simple messengers, they are the outliers, the exceptions that could force a rewrite of the rulebook. Beyond the profound theoretical questions, cosmic rays have a direct and very practical impact on our technological civilization and our ambitions in space. For satellites orbiting high above the protective blanket of Earth's atmosphere, cosmic rays are a constant menace. A single high-energy particle can slam into a sensitive microchip, flipping a single bit of data from a 0 to a 1 or a 1 to a 0. These single-event upsets can cause anything from minor glitches and corrupted data to complete satellite failures, costing millions of dollars and crippling critical communications, weather forecasting, and GPS networks. For astronauts, the threat is even more personal. On the International Space Station or on a future voyage to Mars, astronauts are continually bombarded by this radiation. Unlike the brief exposure of a medical X-ray, this is a chronic, whole-body dose that can damage DNA and significantly increase the lifetime risk of cancer, cataracts, and central nervous system effects. Shielding against these particles is incredibly difficult due to their immense energy. They can tear through a spacecraft's hull like it isn't even there. Truly understanding cosmic rays isn't just an academic exercise for physicists. It is a vital engineering and medical challenge that we must solve to become a permanent spacefaring species. This practical necessity dovetails with their ultimate role as the universe's most intrepid explorers. Because they are charged particles, their paths are twisted and turned by magnetic fields, which normally makes them terrible messengers for astronomy. We cannot simply point a telescope back along their path to see where they came from. However, the very highest energy cosmic rays are so powerful that magnetic fields barely deflect them at all. They travel in almost perfectly straight lines, like microscopic bullets fired from a cosmic sniper rifle. If we can detect enough of them and trace their trajectories back to their points of origin, they could finally lead us directly to the most powerful particle accelerators in the universe. They are our only physical samples of matter from beyond the solar system, carrying a fingerprint of the extreme environments that created them. By studying their composition and energy, we can perform a kind of cosmic forensics, piecing together the conditions inside a black hole's jet or the heart of a merging galaxy cluster. To dismiss them as just high-energy particles is to ignore the most detailed telegrams being sent from the most violent and energetic frontiers of reality, each one a tiny piece of a puzzle that spans the entire cosmos. Yet for all its widespread acceptance, the giant impact theory is not without its own set of puzzling complications, and the most significant of these comes from the very rocks the Apollo astronauts brought home. When scientists analyzed the isotopic fingerprints of these lunar samples, the unique ratios of different forms of oxygen, titanium, tungsten, and other elements, they expected to find a clear signature of the alien world that had supposedly struck us. The thinking was straightforward. If the Moon is primarily made from the debris of this Mars-sized impactor, which we've named Theia, then its isotopic composition should be different from Earth's. Every planetary body in the solar system has a slightly different isotopic mix, a kind of genetic code that tells you where it formed. But here's the stunning twist. For many key elements, the isotopic ratios of Earth and Moon rocks are virtually identical. It's as if the Moon isn't made from a foreign world at all, but is instead made from Earth itself. This remarkable similarity is a massive problem for the Standard Model. It suggests that either Theia was isotopically identical to Earth, a statistically vanishing possibility, or that the entire process of the Moon's formation was far more violent and mixing than we ever imagined, completely homogenizing the material from both bodies in a way that erased all trace of Theia's unique identity. This isotopic conundrum has forced planetary scientists to go back to the drawing board, proposing a suite of alternative and often radical new ideas to explain our celestial companion's birth. One compelling suggestion is that there wasn't just one giant impact, but a whole series of smaller collisions. In this scenario, multiple impactors would have each contributed a little bit of debris, creating a disk of material around the early Earth that eventually coalesced into the Moon. This could help explain the isotopic similarity. If many of these impactors were made of materials similar to Earth's building blocks, their contributions would blend together, averaging out to something very close to Earth's own composition. It's a messier, more chaotic origin story, but it might be a better fit for the turbulent environment of the early solar system, where giant collisions were likely commonplace events rather than singular, dramatic accidents. An even more dramatic alternative is the concept of a cynosure. This idea proposes that the giant impact was so incredibly energetic that it didn't just blow off a disk of debris, it completely vaporized a significant portion of both Theia and the early Earth, creating a vast, donut-shaped cloud of superheated rock vapor that encompassed both the impactor and our planet. In this spinning, puffy, tempestuous structure, the material from both bodies would have been thoroughly and completely mixed together into a homogeneous soup. The Moon would then have condensed from this cloud, while the bulk of the material eventually settled back down to form the Earth. Because everything was blended together in this cynosure, the Moon would naturally inherit an isotopic signature identical to Earth's outer layers. It's a wild and spectacular vision of our world's infancy, a far cry from the slightly more orderly giant impact, and it highlights just how extreme planetary formation can be when unimaginable forces are unleashed. This isn't just an academic debate about ancient history. The outcome has profound implications for our understanding of the entire solar system. The Moon acts as a time capsule, preserving a record of conditions in the inner solar system over 4 billion years ago. If we misinterpret how it formed, we risk misreading that entire chapter of our cosmic history. For instance, the amount of water and other volatile elements found on the Moon provides clues about the conditions in the Earth-Moon system just after its formation. If the Moon was born from a cynosure, it would have started out completely molten and dry, with any water arriving later via comet impacts. If it formed from a gentler giant impact, it might have retained some of its original water. Getting the origin story right is crucial for piecing together the timeline of when Earth became a habitable world. Furthermore, the mechanics of the impact dictate the initial orbit and spin of the Earth-Moon system. Understanding this helps us model the gravitational interactions that have since slowed Earth's rotation and pushed the Moon farther away, shaping the environment in which life on Earth evolved. This is why the new era of lunar exploration is so critically important. Missions like NASA's Artemis program, which aims to return humans to the Moon, and various international robotic landers are not just about revisiting an old destination. They are geological detective missions. New samples from different, geologically diverse locations on the Moon, particularly from its mysterious South Pole, could provide the crucial data needed to break the isotopic deadlock. By analyzing rocks from the lunar mantle, which would have been less affected by later asteroid impacts and volcanic activity, we might finally find a geochemical clue that reveals Theia's true nature or confirms the cynosure model. Each new sample is a piece of the puzzle, and with enough pieces, we can hope to see the full, breathtaking picture of our own planet's most violent and creative moment. The Moon, our constant and familiar companion, continues to guard its deepest secrets, reminding us that the greatest mysteries are often the ones right outside our door. And so we arrive at our final, and perhaps most profound, assumption, one that doesn't just challenge our model of the cosmos, but questions the very nature of our relationship with it. We have long operated under the belief that the universe is an objective, external reality that exists completely independently of us. In this view, human consciousness is merely a passive spectator, a late-arriving fluke of evolution that emerged to witness a reality that would have ticked along perfectly fine without it. The scientist is seen as a neutral observer, peering through a telescope at a distant galaxy, utterly separate from the object of study. This assumption of a clean division between the observer and the observed is the bedrock of classical physics and the materialist worldview. But what if this division is an illusion? What if, at the most fundamental level, the act of observation is not passive but active, and consciousness is not a ghost in the machine but an integral part of the cosmic machinery itself? This radical idea finds its roots in the bizarre and counterintuitive world of quantum mechanics, specifically in a phenomenon known as the observer effect. In the realm of the very small, particles don't exist in definite states with specific properties like position and momentum until they are measured. Instead, they exist in a blurry cloud of probabilities, a superposition of all possible states. The classic illustration is the famous double-slit experiment. When you fire particles like electrons at a barrier with two slits, they don't simply go through one slit or the other like tiny bullets. If no one is looking, they behave like waves, passing through both slits simultaneously and creating an interference pattern on the detector screen behind. But the moment you place a measuring device at the slits to determine which path each electron takes, the wave-like behavior collapses. The electrons abruptly begin acting like discrete particles, going through one slit or the other, and the interference pattern vanishes. The very act of asking the question, which path, seems to force the particle to choose a definite reality. It appears that the measurement itself, the interaction required to gain knowledge, is what brings the particle's potential states into a single, actualized fact. The most common interpretation of this weirdness, the Copenhagen interpretation developed by Niels Bohr and Werner Heisenberg, takes this a step further. It posits that there is no deep reality until a measurement is made. The particle doesn't have a position until an observation forces it to pick one. This isn't just about a physical device clumsily interfering with a delicate system. It's about the acquisition of information. The line between the observer and the observed becomes fundamentally blurred. The universe at its core is not a collection of definite things but a realm of potentialities, and it is through the process of observation that specific realities are drawn out from this sea of possibilities. While the Copenhagen interpretation is careful not to explicitly invoke human consciousness, often defining an observer as any macroscopic, irreversible interaction, it inevitably opens the door to a much deeper question. If measurement collapses the wave function, what ultimately qualifies as a measurement? Does it require a conscious mind to register the result, or is a rock or a camera sufficient? This is where the debate intensifies, pushing into the realm of philosophy. Some physicists and philosophers, like John von Neumann and Eugene Wigner, have argued that consciousness itself must be the ultimate factor that collapses the wave function. In this view, inanimate measuring devices simply become entangled with the quantum system, extending the superposition. It is only when the information from that device enters a conscious awareness that the superposition finally collapses into a single outcome. Wigner even proposed a thought experiment, often called Wigner's friend, to highlight the paradox. Imagine a physicist in an isolated lab performing a quantum experiment. From his friend's perspective outside the lab, the entire system, physicist, lab, and experiment, is in a superposition until he opens the door and asks for the result. Which observation causes the collapse? This line of thinking suggests that consciousness is not a mere byproduct of the physical brain, but a fundamental component of the universe, intimately woven into the fabric of reality. It proposes a kind of participatory universe where we are not just inhabitants but co-creators, our observations shaping the reality we perceive. Of course, this is a deeply controversial and minority view within the physics community. The majority favor less mind-bending explanations, such as the many worlds interpretation, which sidesteps the collapse entirely by suggesting that every possible quantum outcome actually occurs, but in a vast, ever-branching multiverse of parallel realities. In this scenario, there is no special role for consciousness. The wave function never collapses, and we simply inhabit one branch of an infinite tree of possibilities. Another approach, known as objective collapse theories, proposes that wave function collapse is a spontaneous physical process that happens when a system reaches a certain size or complexity, independent of any observation. These interpretations strive to keep consciousness out of the physics equations, preserving the objective, external reality of the classical worldview. Yet, the very fact that we are forced to have this debate is itself revolutionary. It means that our centuries-old assumption of a clean separation between the subjective self and the objective world is no longer tenable at the quantum frontier. The act of gaining knowledge about the universe appears to be an interactive process, a dialogue rather than a monologue. This doesn't grant us magical powers to manifest reality at will, but it does suggest that the universe reveals its properties through relationship and interaction. It merges the domains of science and philosophy, forcing us to consider that understanding the cosmos might also require understanding the nature of the mind that seeks to comprehend it. The cosmic quest, therefore, becomes not just a journey outward to the stars, but an equally profound journey inward, into the mystery of our own awareness and its role in the grand, unfolding story of everything. We've journeyed through 20 core assumptions about space that may be dead wrong, from the expansion of the universe to the nature of time and beyond. Each of these ideas, once considered pillars of our understanding, now stands on shifting ground, challenged by new data and bold thinking. This isn't a sign that science is failing, it's a sign that it's working exactly as it should. Science doesn't progress by clinging to comfortable ideas. It moves forward by daring to ask what if, by embracing doubt, and by having the courage to follow the evidence wherever it leads, even if that path winds through landscapes stranger than we ever imagined. This journey reminds us that the cosmos is far more mysterious and magnificent than any single theory or model could ever capture. The universe is not a static painting to be analyzed from a distance. It is a living, evolving puzzle, a dynamic conversation between our curiosity and reality's deepest secrets. Every time we think we've finally grasped the rules, the cosmos reveals another layer of complexity, another twist in the story. That's not a reason for frustration, it's an invitation. An invitation to keep exploring, to keep questioning, and to remain forever humble in the face of the unknown. As you look up at the stars tonight, remember that you're not just seeing points of light in a dark sky. You're looking at the front lines of a grand human adventure, a story of discovery that spans centuries and continents. Every mystery we've talked about in this video, from the true nature of dark matter to the possibility of a multiverse, represents a doorway. A doorway that someone, perhaps even someone watching this right now, might one day walk through to reveal a truth more wonderful than we can currently dream. That's the beautiful paradox of science. Every answer unlocks better questions. Every mystery solved doesn't close a book, it opens a new chapter. So share your own thoughts and questions in the comments below. What assumption surprised you the most? Which idea fired up your imagination? Let's keep this conversation going. If you enjoyed this journey to the edge of understanding, make sure to subscribe and hit the notification bell so you don't miss our next exploration into the mysteries of the cosmos. Thank you for watching, and never stop wondering. The universe has only just begun to share